So now we have to understand what kind of conditions we need in order that the same conclusion could be drawn to actually go from the conclusion to the conditions. So then we have to consider.
Sorry, you mean the conclusion about the
The conclusion should be that every word that's equal to 1 in the group should contain something like a big part of a letter. So now, when we take the one complement diagram in this case, so we obtain one diagram with two types of regions. The regions that correspond to shorter letters and to the longer letters. So we have big regions and small regions, etc. So here we do the following, we proceed as follows. We define what is called, we define the derived map. So this essay of rank 1. And these are of rank 2. So we will now define the derived map. For this is a ranked map with two ranks. We will define the derived map. How do we define the derived map? We do the following. We look on the distance for each small region. We look on in distance from the big region. For example, this will be on distance 1. This will be on distance 2. This will be on distance 3 of this region. On the other hand, for this will be on distance 1 from this region, on distance 2 from this region, and on distance 3 from this region. Now, then we take for any this one, we take what is the big region that it is the shortest distance to. But it may happen that two have the same distance. Then we order these big cells in some order. For example, this was number 1, number 2, number 3, for example. Then if we have a conflict, so this is a stronger, this is a weaker. So the strong, it belongs to the stronger side. So, and if the distances are different, then of course to the shorter side. If there is equal, then to the shorter. So what happens now? Everything now will be divided in what they call derived regions. So we have derived label. In this case 3. So all these that are closer to this belong to this derived region, etc., etc. So what we obtain in this way is a derived map. Now we assume the following, that if we have a small region, that one of its sides is on the big cell and it has other sides on the small cells. So we need at least 5. So if it is one of its boundary on the big size, and then it is at least 5, one of the bigger side and 5 of the other. So we assume is that this is what we have for this derived, for this what is the relation between the big and small relations, that if some small relation has a boundary with a big map and the rest are small, it has at least 5 small regions. Now, this is an assumption. Why it is reasonable to take this kind of assumption? Because when we look on this, after all, when already but it is semi-canonical, and it cannot have two big parts of small relations inside it. And then we need at least 5 epsilon to have 1. So it means that the common part of a small region and a big region is less than 1 minus 5 epsilon. Therefore, 1 minus 5 epsilon means that this one is less than 1 minus 5 epsilon. So we actually, for a 2 doesn't matter, we need at least 5 regions to be able to complete it, to be an inner region. So we now discuss the derived map subject to 2 conditions. One, the small region has at least 9, either it is at least 9 neighbors of the smallest type, or it has 1 region of the bigger type and 5 regions of the smaller type. But we do not discuss what happens if it is between 2 regions of the bigger size. This can happen. We cannot say that this is possible. We cannot eliminate the situation. Okay, so now we develop the structure of the derived maps under these assumptions.
In the assumptions that you have, does it actually say something about the length of elements in R1 and the length of elements in R2?
Actually, no. This is just what we need from this. This comes from the arguments about the mix, but it boils down to this condition. I mean, there is a
structure. You call them small relators and long relators? It's not something that you require, it's just an intuition.
Yes. Because it's rank 1 and rank 2. Whatever it means, but we need these conditions.
And you have no restriction on the rank 2 one with the other, right? They can
no, actually we need, but we have not stated it. Because, you see, we look what we need to assume in order to reach the conclusion. So the first thing, we have this small cancellation on the 1, this kind of interaction between 1 and 2. And we need, of course, certain interaction of the rest of the bigger rank, but we have not stated what kind of conditions we need. And actually, this condition will appear from the analysis of the derived map. So we look now into the derived map. Now, what we know, if we look on each derived region, then it corresponds to each derived region corresponds to every region of rank 2 in the original map. But now it may have, along with the big cell, also a lot of small cells. because of this condition, I claim we will have the same kind of a layer, a convex layer structure. Let me explain this. So now we are just inside one derived region. And here is the original the big cell of rank 2. So now we have around this maybe many of rank 1. So we hope that this will be also this convex layer structure. The question is maybe it's violated. How would it be violated? So on the first level, on the next levels, so actually if it is convex on the first level, then the argument will go just as it went for the previous case. We have only one type of maps. But we have to check separately what happens for the first level. Because the first level, they may have a contact with a big cell. So, for example, we have such kind of contact from the smaller cell. This is one. Now, we also ask for the minimal counterexample. So, inside this, we would have a normal way of having this. Now, what happens here? They need all of them at least 5 regions. 5 regions, they make 2 on the sides, and then at least 3 on their tops. And this is exactly what we need to prevent the situation that somebody stands here. It cannot stand on more than 2. It cannot stand on 3. Because then it will have 2, not enough. 1, 2, 3, it needs 5. Therefore, we have the same kind of the structure, so we get the top level inside it, we have a contradiction. And it could be also on the first level, immediately, and then also we have it not enough. The same if we have the more elaborate kind of structure of this type, for the same reason it fails. So this condition actually could be improved without, we don't need it, but here we assume that a little stronger that we need for the structure theory, we will need this condition for further use. In any case, it means that also here we have the convex layer structure here until the end of its boundary. And the other will have its own convex layer structure, etc. So then we have to look what happens, is very important, on the boundary between 2 derived edges. So now we look what could happen here. So let us consider this situation. So what are we looking for? Somewhere inside, this is the original pixel, some inside the original pixel. And then we have this convex layers. Now, here we have on this side a sequence of edges along the border. Whatever. We have at least a common edge with the border, and on the other side. Now, let me do the following. In these subsequent regions, I'm just marking the distance to the big values. It could be some numbers that don't know in advance, maybe K1, K2, K3, K4, etc., the distance to this. And on the other hand, I have L1, L2, L3, etc., on the distance to the other thing. So let us check what is possible in this situation. So, let us assume that this is a stronger one, this is a weaker one. So I mean, if it is the same distance, then this one takes it. For example, if we have here some distance, say k, then what is possible on the other side, they may have k to it, or they may have
K minus 1.
chi minus 1. Now, why do they cannot have k minus 2? Because then it would be here k minus 1 to this, and this would take it, so impossible. Also, it cannot have k plus 1, because then it should be also k plus 1 this, and the stronger will take it. So these are just within these possibilities, k or k minus 1 from this. Okay, now, exactly for each of them, this situation. Now, what I'm claiming now, unless we reach value 1, so when the distance is bigger than 1 on this side, or bigger than 0 on the other side, we may not have a weak local maximum. This sequence of integers does not have weak local maxima.
You mean that there are no two with the maximum number?
So there are no weak local maxima unless the value is 1 on the stronger side or 0 on the weaker side. So let us assume, so what it means, a small logarithm, it means that some ki is bigger or equal than ki minus 1, and ki is bigger or equal to ki minus 1. So it is known less than its neighbors. That it is a weak, because a weak local maximum.
You're saying that this cannot happen.
I'm claiming unless the value is 1 on the stronger side or 0 on the weaker side, this cannot happen. So let me prove why it doesn't happen. Assume it happens.
Except for the edges, right?
Excuse me?
Except for the edges, like
K1.
it needs the ki needs to be somewhere in the middle, right? On the whole.
No, everywhere, except that the value of k is small.
No, but K1 is an example of this situation, right? K1 can be larger than K2.
Of course, it is not local.
Yeah, okay.
So what this means is that this sequence is
It is
monotonous?
it is unimodular. It could go this way, unimodular.
Ah,
It could go down, but it never can stop
Mm.
on some place. It goes down, maybe it keeps twice the same value, smaller value, and then goes always up. Unless it reaches 1 or 0 on the sides. So let me do it. So assume we actually do have a local maximum. This one is a local maximum. It means that these are not bigger than them. Both of them are bigger than them. So what it happens that he stands on two neighbors if it is the strong side, because bigger than one. It has at most two on its sides, because these are not bigger, the distance is not bigger than this one, because this is a weak local maximum. So the distance from this to this are not bigger than this. It means that from the point of view of the local, on the convex structure, it could not be outside it. It could not be higher, because this layer is bigger or equal to still these two layers. Therefore, it has at most 4 regions here, right? Or neighbors. 2 below, 2 on the sides. So it needs at least 5 neighbors on the other side, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So now look on this. So this is K, and these are between K minus 1 and K. So we have a sequence of 5 numbers. Each of them takes a value either K minus 1 or K. So what happens? Let us look. So we have 5 numbers. Let us look at the possibilities. So I'm claiming that it will also have a weak local minimum for maximum for one of them. It could not be otherwise. Why? Let's look at the values. 1, 2, 3, 4, 5. What are the possibilities? 2, 3, 4. So if, for example, this is K minus 1. Now, whatever this will be, it could be K minus 1 or K. It could be K minus 1 or K. So if we have this, that whatever this will be a weak local maximum. So it is impossible. Because it is K minus 1, K minus 1, K minus 1 is this will be a weak local maximum. I'm claiming that it is impossible that will not be present a weak local maximum on the other side, because of the restrictions of the distance here. We know that if on this side it is K, then we have 5 regions bordering it on the other side, and it can only be the distance is K minus 1 of K. Because otherwise the map should not go this way. The border would do otherwise. So we know that all the values for this are either K minus 1 or K. So assume for that this was K minus 1. If this is K, then this becomes a weak local maximum, so impossible.
But isn't this what you're trying to prove?
I'm going to prove that one of them should be, I'm going to prove that one of them must be a weak local maximum. And then I will reach a contradiction. So assume there is no, I'm trying to find this configuration that has no weak local maximum. So this is impossible. If we have this one, so this is also impossible, because then it would be a weak local maximum. So we must have this one. Then what could be this one or this one? Both are bad for us. So starting with K plus 1, we gain over. So let us assume we start with K. Then we have here either K or K minus 1. If we have K minus 1, then the same argument leads us to the same thing. Because we have here k minus 1 of k, and then just so it's also impossible. Then we both of the k, the next this of this gives this as well. So we have proven that here must also be a weak local maximum. Assume this one. What happens now? It stands on 2, it has 2 neighbors, it has 1 on the head, impossible.
But is the weak local maximum only have 2 neighbors from the...
To go to me,
Why would it only have 2 neighbors from the there before? The weak...
in the middle,
No.
we have 5 regions.
You
We have shown now that one of the middle regions must be a weak local maximum.
The problem is the other way around. You always have only 2 that are smaller than you, maximum only 2 that are smaller than you. The fact that you have, the only way you can like put more next to you is on the sides,
Oh.
but the fact that you are stuck in the middle is the problem.
Actually, this is a discrete version of a differential geometric fact. Any case, but we have just a easy commutator like that. So what we have now is that unless we reach, let me explain also, what happens when we have the weak side, it may have 1. This needs a special consideration, because if we look on the weak side, and it reaches 1, so, and N assumes that it is a weak local maximum, which we claim is impossible. So assume it is. When it is 1 on the weak side, so on the strong side, it could be either what? Either 0 or 1, right? Because it would be 2 on the strong side, it would be 2, so it is either 0 or 1. If it is 0, well, we adjust to the ordering. If it is 1, then it should be, here we have 1, 2, at least 3 here, right? Because it needs 5, 1 on this, and we need 5 here on the side. So these are 5. 1, 2, 3, 4, 5. Now, what happens on the 1? This is the strong side. What happens now? This one in the middle has 1 of the bigger side, and it have 1, 2, 3, not enough. So this is also possible. But it should, because now we use just this 1, 5 condition, it's not the 9 condition. So we have to look at separately. So what actually happens? One of the 2, this minimal, so because it's only model, it reaches its minimum in 1 or in 2 places. What this minimum could be equal? It could be bigger than 1, or equal to 1, or be 0. So if it is bigger than 1, then somewhere we have it, someplace. Maybe 2 at the smallest value. Then it means it may be some S and S plus 1, S plus 2, S plus 3, etc. S plus 1, S plus 2. It should go equal. Any other behavior will contradict our assumption we do not have weak local maximum. Because if we do the same, the next one, this becomes a weak local maximum. If it doesn't increase, it cannot jump by 2. So this is a very definite possibility how it behaves. Now, I have to introduce the following concept. When we are looking on this derived map, so actually we have here, for example, derived regions. For example, here we have 3 derived regions. For example, now they're asking whether, what does it tell us? This is long, this is short, we don't know how to measure it. So we introduce the following idea how to measure it. We remember on each side we have a convex layer structure. So we have a convex layer structure on this side, etc. Now, for every point in the convex layer, we can take what we call the left transversal and the right transversal to this origin. What it means? Assume I'm in this position, here. So I may go to the left or to the right until I met some edge. Then I going again here to the left until I met some edge, etc., until I will meet after all the big cell. From this was this way. Now I could do consistently the same to the right. I go here to the right. Now the question is, what happens from the point of view of the local structure? What I'm saying is that always it will see it, they cannot go distant from one the other. Why? Assume, so first it cannot be 3 regions between them. Why? Because this one would have not enough of a stop. These 2 below for the sides. So it means that it should come only as, excuse me, this is 1, this is 2. The next one should repeat the situation. Why? Because here it is of 2. If here would be 3, whatever the position, this one is 2 down, 2 on the sides, and 2 here is not enough. And even if this is 0, then it will be 1, 2, 3, 4, not enough, we need 5. It's situation, but we need 5 here. But if this is a big cell, still we need here all 3 could not be here. Because 3 means that this middle doesn't have enough neighbors.
Only 2, right?
This one have one of the big cell. This one big cell, and 1, 2, 3, 4 neighbors of the smaller kind. We need 5. So it means that whatever we consider these transversals, they never go apart more than 2 regions. Okay, now look here. What happens here, that I'm looking, going from this point, taking the right transversal. So I know that now this is smaller distance, so it has to go here. This is just the free fall of it until it reaches this point. And then it goes here. Now, what happens with this? Whatever. What I know, it stands no more than 2 regions. Because the distance, this is the left transversal, this is the right transversal, it could not be, the distance between them, because of this argument, cannot grow more than 2 regions. You see? This is a layer structure. Because this is it could not be the same. This is with level 3. So just we go down by the level, down was the level, down was the level. 34, we just reach this and go here. The other transversal, whatever it does, must have here no more than 2 regions. The same from the other side. So one transversal goes this way, the other goes here and has no more than 2 regions here. It means that we take down the transversals from the boundary, the left transversal on this side and the right transversal on this side. So we know that here we have no more than 4 regions. It means that if we measure in this way the common boundary, just as a projection on the original big cell, just taking the left translate on this and this, then we measure here, it could be no more than 4 points for the small cell, which was assumed that these cells are small, it will be a small part of it. And the same for the other, because absolutely the same argument will happen for the other also 4. It means that when this distance is big, the minimum is bigger than 1, or 1 is bigger than 0 the other, so it means that when we measure the common part just by the projection on the original big cells, it will be small. So what is the only possibility that escapes this mechanism is the following. That we may have a situation where if this is the strong side, this is the weak side, the strong side will take it this way. So we may have here a sequence of regions that have on the both sides of it. And then when we try to do the same, the projections on both sides, so we have the left transversal here, the right transversal will reach this one, so we may have here 2 regions. On the other side, the left translation, the left translation will be there, the right translation here, we have here also 2 regions. So what happens now? We have 1, 2, 3, 4, but we have here this sequence of regions of a smaller kind, in principle may be very long. So this is called the contiguity diagram. So in general, it means if we do not have a way to take control over the contiguous, then we stuck here. Now what happens? We now assume that both of these original big cells are cyclic, what is the canonical form. And then we know that in the canonical form, it should be, all of them should be close to, if there are to 1/2, because otherwise, no, excuse me, let me say this way. So, could be just a sequence of this. It could be a situation that is a number. It need not be connected as I showed. It could be part of them exists this way, then they coincide, some other goes this way, whatever, and then they go this way. So maybe 2 additional on this side, 2 additional on this side. So I mean that this one region is, as I draw here, the other one may be this way. So I mean that this need not be just a connected sequence. in any case, we can consider the maps, the chart on the both sides. We have a chart on this side, a chart on this side. Of course, these are, of course, members of the chart. And when the members of the chart, they are close to 1/2. Because what happened, each of them was a winner in its competition. If it would be much bigger than 1/2, it never would win its competition. Because taking the canonical form in the third step, we just compute the lengths. Look, and then if it length is much bigger, then the other side would definitely win. So it means that in any case, all this should be somewhere along 1/2. Plus means some few epsilons. Here it is. Now, let me ask, how can it be that for this was the winner, and for this was the winner? So let us go into the steps of taking the canonical form. First, it is semi-canonical is okay, but the second will be the certified. I'm claiming that because of this legend on this side, common, and this, so this was the beginning, and this one on this side, everything between this will be the same certified map, whether I judge it from the position of one cell or the position for the other cell. Why? Because to establish the fact of being belonging to the certified map, we need witnesses. And this cell could be used to intercept the witnesses and to convert it to the witnesses for the other side. Because they are close to 1/2, so they are far from this concept number 1, whatever it does, I can take it to the safe haven. So it means I just step 1 inside it, and from this to this we have the same certified map. Now, then we need the local competition. The local competition will be the same, just stepping 1 more from this, because it is a border of the certified, so it may be here. It will have just a, here, excuse me, from this, okay, this is certified. Now, from next one, it is a neighbor that is also certified on both sides. So stepping 1 less, so then it must be the same outcome of the competition for both sides. Therefore, we cannot have this will disappear, and then we have just the common boundary between these two sets.
So it's still 4.
Huh?
So it is still 4.
It is?
Still 4, the number of...
Oh yes, no, it is 1, 2, 3, 4, 1, 2, 3, 4 on one side, 1, 2, 3, 4 on the other side. This is for the discrepancy between the transversals. This for taking the intercepting the witnesses, and then for taking the for this inside the certified. Just this is the side because it needs the same local condition. So 4 on this side, 4 on this side, and here we reach the direct meeting between the big cells. Because we assume we're taking the canonical form of the cyclic words. So then, what we need, we just have, now this word will be in a certain combinatorial pattern of the words, periodic or whatever, and then they cannot have a direct meeting because of their combinatorial structure, or just we impose that this will be small part of this. So what happens? Then we say, if we know this be some epsilon 1 for the big ones, plus actually 8 regions on each side. And then all of this together will be some small epsilon 2 of the common length. Then in epsilon with less than 1/9, so as a result, the derived region also will have the same properties. In region, in the derived region, will have at least 9 neighbors. And then we'll have the same kind of convex layer structure. And then something happens on the highest store of it. Either it is the original big cell or with some layers over it. And when it has some layers over it, it also has the highest store. And then either the original rank 2 cell will have a big part on the boundary, or one of the small regions will also have a big part of the boundary. So this is in very short, but in essential moments, what will be the small cancellation for rank 2, that we have 2 different types of maps and we need certain cancellation conditions between them. Now, then, of course, now we stop. The next will be to generalize it to the rank n, but it seemed a formidable task, but it turned out in the discussion that we had with Agata, that actually everything boils down